All right, cool. Okay, perfect. Okay, hi everyone. My name is Maz. I'm part of the Mechanism Labs team. Today we'll be talking about Ouroboros, and we'll be going over the different iterations of it. Um, as you know, as some of you might know, Ouroboros was it's a project under IOHK. They have different initiatives, and it's the protocol that's powering Cardano right now. So a little background on Ouroboros. I actually found this out recently. The word Ouroboros is the symbol of Ouroboros is actually a serpent, like a snake eating its own tail. It supposedly originates from ancient Egypt, and it kind of symbolizes cyclicality and like reiteration and recreation. So it kind of fits well with how IOHK has been going along with their process, because they've released different iterations of the Ouroboros protocol at different stages. So they first had the original Ouroboros paper, then they had Ouroboros Praus, and recently, a couple of months ago, they just had Ouroboros Genesis, and they plan on having a new one called Ouroboros Hydra that I think will be coming out and sometime in 2019. And as Charles Hoskinson put it in one of his tweets, the original Ouroboros was all about theory, Praus was practicality, and Hydra is going to be performance via sharding. So that's sort of how he plans, well, they plan to kind of scale Ouroboros to match a large number of users. So the original Ouroboros paper was originally conceived as a proof that proof of stake could be properly secured. You know, like in the beginning with Bitcoin, proof of work was, you know, a lot of people claim that proof of work was like the main dominant Sybil resistant mechanism. And the idea of proof of stake came along, but there were a lot of disadvantages with it. You know, there's the nothing at stake problem, there's the long range attack, and people thought proof of stake systems couldn't be secured. So Ouroboros was one of the first ones to not only write a proof of stake protocol, but also have it peer reviewed in a properly academic process. So the original paper talks about they use the cryptographic primitive they use in the original Ouroboros paper is called the publicly verifiable secret sharing mechanism. And what that does, okay, so before that, first of all, Ouroboros is a proof of stake based protocol, and it's more chain based. So uh, there are two types of proof of stake protocols. One's chain based, one's BFT based. Chain based protocols resemble Bitcoin, where you have some kind of voting mechanism to generate blocks, and blocks are probabilistically finalized. Whereas in BFT, you have PBFT run on the blocks, and they usually have absolute finality depending on the implementation. And so in Ouroboros, the way someone is elected to be the one who proposes a block is through this publicly verifiable secret sharing mechanism. And the way they do it is they have all the shareholders in the protocol undergo a cryptographic coin flip on the blockchain. So they have to essentially generate a secret number that they have to publish to the blockchain. And the protocol itself will take the those random outputs from the different stakeholders and use those numbers to create a randomness seed that everyone will then use. That the epoch that determines the stakeholders in the next epoch. So the way it works is in the current epoch, everyone, does this coin flip mechanism. They generate some number and put it on the blockchain. Then by the end of the epoch, the protocol uses all those random numbers to figure out who the next block producers will be in the next epoch. And an epoch is just some period of time. So in the original Ouroboros paper, that was 10K blocks, so 10,000 blocks. So every 10,000 blocks, they would redetermine who are the block proposers. And the problem with having all the users publish their secret numbers to the blockchain is that it really causes a lot of overhead. So imagine like you have n number of participants in the protocol, and each one of them publish um, has to publish whatever secret number to the blockchain. This can cause a lot of congestion in the network, and it can take up to n squared messages just to uh, just to determine who the next block proposers will be. And because of this large overhead, the original Ouroboros paper actually had a minimum stake limit. So similar to some other proof of stake protocols where you have to have like a certain number of native currency to be a block proposer, Ouroboros also had that. But the problem with that is that it leads to um, the necessity of delegation. Not everyone can be a block proposer, and so the ones with lower stake will have to delegate their voting power to someone else. And this could be exploited by an attacker who could potentially socially manipulate those low stake users into giving up their voting power and kind of break the system. So Ouroboros Praus, which was released last year, builds upon this by using a VRF, which is a verifiable random function. So a VRF, the way it works is you use your private key and some input to generate a pseudo-random number and a proof. And the way Praus does it is any stakeholder uses their own private key and a nonce that's determined by the protocol to determine whether they're the block proposer or not. So it sort of happens like a lottery system where you generate this random number, the pseudo-random number, and if you're underneath some threshold value, then you are a block proposer. If not, then you're not, and you kind of move on. And this was a huge improvement in the protocol because after this, people could then, like, there was no more need of a minimum staking limit. So anyone with any amount of stake could become a block proposer. But this also led to the possibility of multiple leaders per block or no leaders at all. And in the case where there are no leaders, it just resembled an empty block, and you kind of moved on from that block, which is being an empty block. And because Ouroboros, their system operates in a semi-synchronous way, that was fine because you had some upper time limit on how long you would wait for the block to be proposed and or verified. And so if no one was a block proposer, you would just move on to the next slot, which is essentially the block. And in the case where there are multiple leaders, this could create a short-term fork. But the way Ouroboros dealt with this was similar to, in some cases, Bitcoin. You kind of just go with sorry, not Bitcoin. Bitcoin doesn't do this. But the way they dealt with it was whichever block you saw first was the one that you adopted. And so it was kind of like a network effect. And depending on like the topology, like certain users had like a more tightly knit network, then those users would have a better chance of having their block propagated and accepted into the network. And the nonce that's used in that VRF, it comes from the values of block headers from the previous epoch. So in original Ouroboros, the randomness was generated by publicly posted numbers from each user, which caused a lot of overhead. But in Praus, there is one common nonce per epoch that everyone uses. And that nonce is regenerated at the end of every epoch by using block headers from the current epoch.
Does the protocol have a concept of block time? Because if not, if there's no minimum block time, then and you try to proceed at the speed of network delay, then you're bound to get lots of forks.
Yeah, so they do have a sense of time. The original paper operated in a synchronous fashion, but Praus and Genesis both operate in a semi-synchronous fashion. So they assume there is some like upper limit on like how long a block time is, not block time, but like a round time, like a slot time. So that's why in the case of no block proposers, sorry, you can kind of get past that by kind of timing out.
Okay.
Yeah.
Cool.
And another advantage of having a VRF instead of the secret sharing system is that block proposers are not known ahead of time. So this is somewhat similar to how Algorand works, where that if you run your VRF and you generate this number that shows that you're a block proposer, you don't need to reveal that you are the block proposer until you publish the block. And this is a strong security advantage because it mitigates the possibility of a DOS attack on block proposers, whereas in the original paper, block proposers were deterministically known at the beginning of each epoch, and it was possible to DOS them or kind of just like, attack them in some other way.
Does this mean we're not unsafe in asynchrony then? Because you can get multiple forks resolving due to these randomized proposers.
In asynchrony or synchrony?
Are we unsafe in asynchrony?
So
now we'll have these multiple paths.
Yeah, they don't directly talk about asynchrony, but I would assume so because they kind of rely on timing assumptions to kind of get past the different block times and block proposers.
Huh. Okay, thanks.
Yeah. And so Ouroboros Prouse also protects against, they assume an adaptive adversary that is able to, that has a large amount of stake, but which is still in the minority. And that adversary also has a dominant control over the network. So because it's in a semi-synchronous setting, they assume that the adversary can delay messages within the system up to some delta time, but those messages must be delivered eventually. So even though the adversary can, delay which blocks are shown to certain users, eventually all blocks will be shown to those users. And so recently, about a couple months ago, they came out with the newest iteration of Ouroboros, which is called Genesis. And this is essentially just a new version of Prouse, but instead of relying on what was it? Yeah, so the way they determine which chain to continue to build upon is the novelty that comes through Genesis. So the idea is that previously in Ouroboros Prouse, they would choose the block, whichever block was first seen by them. So whichever user proposed the block first, that's the one people would adopt and build off of that. But in Ouroboros Prouse, they have a new chain selection rule. And they kind of get this idea from the idea of how proof of work operates in Bitcoin. Because in Bitcoin, people choose the chain with the highest difficulty of hashing power. And similarly in Genesis, they use a new chain selection rule that uses densities of the chain. And I'll talk about that a bit more. But first, I'll tell you the main reason why they want to consider this. So the problem with Prouse and many other proof-of-stake protocols is that because you have people staking native currency, the mechanism is all on-chain. So it's virtual currency. There's no physical resource that prevents people from potentially voting on two different chains. So the nothing at stake attack was a prime reason why they continued their research on this, and to prevent the nothing at stake attack, they had to come up with a new idea of how to resolve chain selection, and what they did was first they identified what environment they wanted to work in. So the environment is something they define as dynamically available. And in this environment, they wanted to consider the situation where different users can join and leave the protocol at will. There's no assumption on the number of online and offline parties, because people can lose synchrony, they can lose connection with the network, so you can't be sure of how many people are participating, and we can't be sure of the participation levels of any nodes, whether they're continuously voting, whether they're continuously proposing blocks. So the way Ouroboros Genesis does it is they have this chain selection rule that operates in two scenarios. In short term forks, they just accept the longest chain rule. So it's similar to a lot of other common proof of work chains or proof of stake based or proof of stake chain based protocols, where you just go with the longest chain up to a certain k number of blocks. But in the case where you have more than k blocks, where you have a fork more than k blocks away, a lot of protocols had different approaches to this, because this gives rise to the long range attack. And in the past, different protocols used checkpointing as a means to secure against this, because with checkpointing, you kind of, have this cemented block where beyond that, you can never revert beyond that point. And even with that case, that still requires trust, because if there is a new node that enters the network, they can download the blockchain, but then to verify the checkpoint or whatever, they need to get that block from some other user, some other person, and that requires some level of trust. So the way Genesis does it is they're able to bootstrap the entire blockchain just from the Genesis block. And they do this with their new chain selection rule, which is based upon chain density. So whenever there is a fork of more than k blocks, they look at the point where the fork diverged, and from there to the current block, they split that whole time frame into different regions and look at each region and kind of consider the density of blocks on the different chains. And the idea is, when there's an adversary that proposes a fake block, the number of blocks that come right after it are lower in number than on the main chain, because all the honest users, which are assumed to be the majority, will continue to operate on the main chain. So there's a denser there's a denser population of blocks. And so sorry?
Oh, doesn't this introduce a couple problems though? Like if you're going by block density, now every proposed block that's not going to be the main block, it has to be included as a tip in the next block state.
Okay.
But then you also get a problem where now any previous set of people, if right now in most proof of stake systems, you have to worry about the current validator stuff being corrupted. But but in here, if I go buy a ton of old accounts from us 10 years ago that are now empty, I can then produce a ton of blocks in that time range, and increase my fork. I can make my fork the main one. Because block density is just tied to the amount of stake at a point in the past, not at a point in the present.
Yeah, but they do assume an honest majority, right? So even if you did buy up a bunch of different accounts and you went and from the Genesis block tried to create your own chain, you wouldn't have as much voting power as the honest majority, right?
But it's an honest majority of people who are doing this grind or this mine function, who have the server dedicated to this. And also suppose that 10 years ago I had a ton of money. Now I've all moved it to new accounts. I just sell those old private keys because they're worth nothing.
Yeah.
Yeah. Ouroboros doesn't assume honest majority of it doesn't assume rational majority, like where it's like people have only of the people who have like stake. It's like honest majority of everyone at all points in time in the past.
Oh, okay.
Yeah.
A strange assumption. Okay, thanks.
Yeah, no worries. They have a proof in their Genesis paper about that. If you want to check it out.
Will do. Thanks.
Yeah, definitely. So yeah, as I was saying, yeah, Genesis uses the density of the chain after a fork, whichever chain has a higher density immediately after the fork, that's the chain that people are are led to adopt by the protocol. And so far, that's where Ouroboros is in the iteration of protocols. So from the original Ouroboros paper up until Genesis, they have been able to kind of implement a strong feature in proof of work that helps proof of stake become more secure. And it kind of avoids the necessity of having both a minimum staking requirement and checkpoint blocks, such that new users can bootstrap the whole blockchain just from the Genesis block. And they also do this based on the randomness seed that they have, because at every epoch it's like they can determine it based on the epoch randomness that changes over time. And so for new users, it's pretty easy to ramp up with the new blockchain, but to synchronize into the network, it takes a bit of time, and that will happen as the new user participates in the network. And yeah, so one main thing that when we analyzed Ouroboros, we looked at was that they had a bit of an incentive scheme outlined in the original paper. They didn't really mention any improvements on it or anything about it in Prouse or in Genesis. But recently, less than a month ago, actually, they came out with a new paper called the Reward Sharing Scheme for Stake Pools. And the idea is that they want to create fair formation of stake pools to kind of go with the large number of participants that would be in their protocol. And this is really good because it incentivizes protocol adherent behavior, and it also helps protect against potential Sybil attacks, which kind of works on top of proof of stake. And they have a proposed reward scheme, and they in that paper, I haven't gone through the whole thing, but I was skimming over it, and in that paper they also ran some simulations with varying costs and rewards based on the different parameters they had for their reward scheme model, and they showed that they were always able to reach Nash equilibrium, and that the protocol would stabilize at around 10 staking pools with about equal number of stake. And there was also a recent AMA that Charles Hoskinson did, where he kind of talked about Ouroboros Hydra. He didn't go into too much detail about it, but he did say that they plan on using some form of sharding and implementing sharding to kind of leverage the large number of participation to allow the protocol to scale appropriately. And Hydra is planned to come out in 2019, and as usual, they have some of the top researchers on it, and they continue to use rigorous academic peer review process to publish their papers and the sort. And yeah, that was basically an overview of Ouroboros, from the original to Prouse to Genesis, and hopefully to Hydra and the reward scheme. Are there any questions?
Could you explain a little bit about how the Ouroboros Prouse works and how it does chain based in a partial synchronous setting?
Yeah, so they basically have epochs, right? And each epoch, for Proust, they said the epoch would be about 24,000 blocks. So the way it works is in between epochs. So for any given 24,000 blocks, they kind of assume that the stake is static, and they have different proofs um, in both the original Ouroboros and Proust on how static's model works. And like I said, at the beginning of each epoch, there's a randomness seed, a randomness nonce, sorry, that everyone in the protocol uses for their VRF. And for each block, everyone kind of does that lottery system via their VRF to determine whether they are the block proposer or not. And if they're chosen, they create the block and they publish the block with the proof generated from the VRF to show that their block is valid. Um, and so this goes on for 24K blocks. Then by the end of the epoch, I think it's around near the last third or the last like 2 to 5,000 blocks, the protocol generates the new randomness nonce using different proof values from previous block headers in the current epoch. And so the randomness nonce can't really be predicted until at least the last few blocks in any epoch. And even then, it's not all the proof values that are chosen. It's some random number of them. And so this also creates another level of randomness that can prevent, kind of predicting who the next block proposers will be in the next epoch.
But I don't understand how that allows it to be partially synchronous. Like, in the very worst case, like, isn't there still a synchrony bound at like the whatever the block time times 2048 or 2048, I think it was, blocks? Like, isn't that still like a synchronous bound?
Yeah, I think the way they meant that it's semi-synchronous is that you have an adversary who can cause network delays. And so you kind of have to factor in for that because the adversary can kind of, like pick and choose what messages get delivered, which ones don't. But by the end of any round, I think they have to get delivered. So I think that's why it's semi-synchronous and not synchronous. Does that make sense?
That would make it synchronous if there's like a time limit for a round, and then like it needs to have
the distribution. So it's like weaker than partially synchronous, slightly stronger than synchronous.
What does that mean? Can you explain?
Oh yeah, semi-synchronous just means the distribution of the value that the time delay can be, but you don't necessarily know exactly what that value is. Versus with synchronous,
so you don't know that there's an upper bound though.
Well, the upper bound. You know the distribution of the upper bound.
Okay.
Wait, the upper bound's now a randomly determined number?
Yeah, but the distribution of like what the upper bound values could be.
So is this a weaker model than partial synchrony then?
What? No, this is not partial synchrony. This is semi-synchrony. Partial synchrony, you don't know the upper bound.
In partial synchrony, you say that there is a fixed upper bound.
Yes, there is. Yeah. So in partial synchrony, there is a fixed upper bound, and you know the value. No, you don't know the value of it. In semi-synchrony, there is a fixed upper bound, but you know the distribution of what values the upper bound can be.
Huh. Interesting.
Yeah. This is like very tricky language where you make it sound like you're partially synchronous, but you're not.
But you're not.
It's like we're more.
Pretty sure Charles uses like the term partial synchrony, and like this is what Vitalik has been like shitting on him for all week, where it's like, yeah, this is not partially synchronous at all.
Because like I don't know if Charles understands the technical part of it. Which is why, like, the paper only uses semi-synchronous. Never ever do they use that term partially synchronous.
On Cardano's marketing materials, they use partial synchronous.
Because at that point, they just converted semi into partial, and it was like,
This seems kind of weird though, 'cause if you're having like network delay problems, right? You can't just adjust the distribution which you know. Like the 90% partial synchrony is right. Like if you don't meet your partial synchrony assumption, it's trivial to detect, and you just increment the timeout. But you can't really adjust your semi-synchronous model because the whole point is you're saying you already know the distribution.
Wait, so are you saying that it should always be some fixed upper limit?
Well, maybe I'm confused here, but like, so partial synchrony, right? When we're running into issues with our knowledge being wrong, we just say, okay, we're going to increase our number, our timeout number, because you can do that. But with the semi-synchronous model, I'm not sure how you detect that your assumption is first wrong, and then how you detect and how you remedy that, because you're saying you already know the distribution.
Okay, I see what you mean.
If you know
But I'm not.
if you know the distribution, there's either two scenarios here, right? Either you know that there's like, so let's say you know the distribution, you know that it doesn't go like the maximum doesn't go to infinity, in which case it's a synchronous protocol because you could like put your max network delay at just above that maximum. Otherwise, the other alternative is that there's a tail distribution in which you know there's a chance that there might be a network delay that goes to infinity, in which it's an asynchronous situation. So like I don't understand, like semi-synchronous seems like if you knew the distribution, you would know whether it's in a synchronous or asynchronous setting.
Yeah.
Okay, yeah, that makes sense. Let me pull it up because
Is semi-synchronous a term used in like distributed systems literature? Because I've never heard it before.
Yeah.
Oh, is it a normalist thing?
It is used in distributed systems, but it's not like super common.
Okay.
I just don't see why how being a semi-synchronous system doesn't automatically let you know whether it's a synchronous or asynchronous. In fact, semi-synchronous and partial synchronous seem to be completely like opposites.
Well, it might be that semi-synchrony is a stronger thing than, weaker than synchrony. Because in synchrony, you're saying there's a strict ordering, whereas with semi-synchrony, you're not implying a strict ordering. I'm saying like every message will arrive in like a constant, like in 10 seconds plus a uniform RAM number between 0 and 10 seconds. So you still get some weird reordering effects.
Right.
yeah, I think that's kind of how it's modeled because based on like the adversary, they say he can delay it up to some delta amount, so it's not a fixed amount, and he can always like choose what amount that would be. So yeah, there would be some reordering of how that would go.
So like this is kind of like what Vitalik's post like about like so the synchronous like if you assume that all messages arrive in order like perfect synchrony, then that's that whole thing he did about the 99% fault tolerance consensus. And so then I guess like what you guys mean here by semi-synchronous is sort of what like proof of work kind of already is, where like messages aren't guaranteed to arrive in order, for example. So it's kind of like,
Yeah, with fully synchronous messages around with synchronous messages don't necessarily need to arrive in order. Semi-synchronous also no order. Semi-synchronous is like between synchronous and partially synchronous.
So would proof of work be semi-synchronous, right? Not synchronous.
Yeah, because it's a Poisson distribution or geometric distribution. My bad. Of the block times, etc.
Yeah, it could be. It might be semi-synchronous.
Okay.
All right. Yeah, that makes sense. Are there any other questions? If not, okay, then I think that wraps up today's community call on Ouroboros. This one will be posted as well on the Telegram. So if you ever want to check it out again, go over it, go over some of these discussions, you can. And if anyone ever wants to start a discussion about some of the things we just talked about, feel free to, also on Telegram. Yeah, until next time. So next community call should be in 2 weeks as well. We will tell you guys on Telegram and or Twitter what we'll be talking about next.
Thanks for the explanation. It's pretty cool to understand how it works now.
Yeah. And we have some exciting projects coming too. So hope it'll be good. All right.
Awesome. Thanks for the explanation, Moz. Thanks everyone who made it to today's call. And see you guys in 2 weeks.
All right. Bye, guys.
Bye. Bye.
Bye.